So today we're going to look at buffers, and buffers are a way of having a solution that resists changes in pH. So buffers are made by mixing either a weak acid or a weak base with a salt that contains the conjugate of that weak acid or base. It's common to have an equal amount of both the acid or base and its conjugate. However, you can vary the amounts so that you have different buffering solutions. And each buffering solution is designed to maintain a specific pH level. There are many natural buffers. We have buffers in our bodies that make sure our blood is maintained at a specific pH. Really important to a lot of our biochemical processes. We have buffers in our cells, we have buffers in our plasma. A lot of acidic foods that we eat, like yogurt or sour cream, or even medicines like aspirin, have buffers in them in order to ensure that when you eat those foods, you're not going to have a large change in pH in your body. Again, why no change in pH? Because we need to make sure that enzymes are functioning and they operate in a very narrow pH range. If you look back at the titration curves that we studied last day, you'll notice that there are some straight regions in the titration curve. Those straight regions are what we call buffer zones. They're regions where the pH is not changing very much. If you take a closer look at the buffer zones, you'll realize that at each of the buffer zones, it actually has half the volume that's required at the equivalence point. Well, why half the volume? Because if we have half the volume of the equivalence point, then we actually have a mixture, equal amounts of both a weak acid and its conjugate base, or a weak base and its conjugate acid. So in other words, we get that buffer zone because we've got the exact conditions we require to make a buffer solution. We can reconcile this with everything we've been learning about Bronsted-Lowry theory and Le Chatelier's principle. You can see the two conjugate base pairs there, both the acetate and the acetic acid, the water and the hydronium. So what normally happens when we add an acid to a solution? If we add an acid, it's a source of hydrogen ions. If you look at the strong acid, hydrochloric acid, complete dissociation or ionization. So we're going to get a huge influx of hydrogen ions that's going to increase the concentration and correspondingly decrease the pH. But what happens if we add an acid to a buffer solution? Remember that the buffer solution contains the conjugate base acetate. So when we add the acid, it's going to react with that conjugate base. Remembering that neutralization is a one-way reaction, that reaction with the conjugate base is going to consume the acid, and because the acid is being consumed, we're going to have very few hydrogen ions being released, and so we're going to have very small change in pH. Even though it's creating more acetic acid in the process, remember that acetic acid is a pretty weak acid, so it's not going to ionize very much. So we've got the acetate ions reacting with the hydrogen ions from the acid. It's going to drive the equilibrium to create more acetic acid. So what happens is we have most of the hydrogen ions being removed. Obviously, not all of them will be removed. There'll be a really small change in the pH, but nothing like if you didn't have a buffer. And we'll back that up with calculations in a few minutes. What happens if we add a base? Again, with no buffer, adding a strong base that's going to be a significant source of hydroxide ions. It's going to increase the concentration of hydroxide ions and consequently increase the pH. If we add a buffer, when the strong base is added, it's going to react with the acetic acid that's present in the buffer. Again, neutralization reactions are one way, so that is going to consume the base. It's going to create sodium acetate, and so since the hydroxide ions are being consumed, again, we get very little change in pH. You can see that reaction happening there. You can see how it's shifting the equilibrium, and you can see how the hydroxide ions are being consumed. And this buffering action occurs until finally it can't happen anymore, and at that point you'll see a dramatic pH change. Also realize that from the equilibrium mixture, it's going to create more hydrogen ions. These hydrogen ions are also going to consume hydroxide ions. And so again, every time these hydroxide ions enter the solution, the buffer solution, they are being consumed and we get a minimal change in pH. So we've talked about it qualitatively. Now here's the quantitative backup of what we've been talking about. So suppose you have a 1 liter buffer and it contains a 0.55 molar acetic acid solution and a 0.50 molar sodium acetate solution. So we've got this buffer solution, weak acid, salt containing a weak conjugate base, and it says calculate the pH of the buffer. Because it's weak, we're going to throw in our ice table. Initial concentration of the acid, we got from the question. Initial concentration of the acetate, we got from the question. And then we do our ice table. Concentrations are going to go down. You can see the equilibrium concentrations, and we're going to plug these into our Ka for the acid. Plugging that in and using the 100 rule, solving for x, we find out that x is 2 times 10 to the negative fifth, and that is the hydrogen concentration, so we'll use that to work out the pH in the negative log. So we've got a pH of about 4.7. There's a quicker way of working out the pH of a buffer solution, and it's called the Henderson-Hasselbalch equation. This is simply derived. I'm going to show you how it'll be derived here so you can understand that it comes from equilibrium principles. But after its derivation, I'm just going to ask you to be able to use the equation. So looking at an equilibrium mixture that contains an acid and the conjugate base, again, both of them weak, so we're using equilibrium constants and ice tables. You can see the equilibrium law there. If we rearrange that equation, we have an equation for the hydronium concentration. It would just be equivalent to the Ka times the acid concentration over the concentration of the conjugate base. Now, if we were to take the negative log of both sides of that equation, it would look like. And realizing that the negative log of the hydronium concentration is just the pH, we can switch this equation to look something like this. The pH is going to be equal to the pKa, again that's the negative log of the equilibrium constant for the acid, plus the log, and you'll notice that we've switched the signs here. Instead of adding the negative log, we're going to add the inverse log, so you can see that we've swapped the location of the anion concentration and the acid concentration. So that's the Henderson-Hasselbalch equation. Really saves you time. So let's look at the same equation that we looked at before. Okay, using our equation, exact same equation, plugging everything in, and you'll see we get the exact same pH as before. So nice short way of determining the pH of a buffer solution. So let's look at this buffer solution, and suppose we add 0.10 moles of strong acid. This is a monoprotic acid, so 1-to-1 mole ratio of acid to hydrogen ions. If we're adding 0.1 moles of the acid, the hydrogen ions are going to react with the acetate ions from the buffer. That means it's going to act to decrease the acetate concentration, and consequently, or subsequently, it will increase the acetic acid concentration. How does it change them? Well, remembering that we added 0.10 moles of acid, it's going to react, and so it will decrease the acetate concentration by 0.10 moles. The acetic acid is going to increase by 0.10 moles, and so we have the number of moles present after the strong acid reacts with both of the components of the buffer. Remembering that it was a 1 liter solution, we can convert these molar amounts to molar concentrations, and then we can just plug them into the Henderson-Hasselbalch equation. That means when we've added 0.1 moles of a strong acid, the pH of the buffer was initially 4.7, and even though we've added a strong acid, the pH has only gone down by 0.2. That's a very small change in pH. If we had added 0.1 moles without a buffer, the pH would have changed to 1. So you can see, again, remembering each pH change of 1 represents a 10-fold change in the acid concentration. Going from a pH of 4.7 to a pH of 1 represents almost a 10,000-fold change in the acidity. So clearly buffers are doing their job. What you can do to practice, again, we'll work on these in class. So these are the questions from your textbook that we'll be working on. So there you go. That's your background. Look forward to doing the labs in class with you next day.